this case, this is composed of three basic shapes, the ABCD, BCEF, and BEH. So these are the three basic shapes in this plane geometry diagram. So first we define a set of basic shapes, which can be seen in the appendix. These are the set of basic shapes that we define first. So after that, we pick one of these random shapes and we attach one more shape from the set to a side of the randomly chosen shape. So we can say, for example, pick this one and attach it to this guy out here. So that'll help us generate another diagram in plane geometry. After that, we'll just label the vertices with A, B, C, D, and we'll label certain specific angles inside the diagram. So this is how it generates a plane geometry diagram. It does a similar job to generate an analytical geometry diagram. For example, this one. The third image is an analytical geometry diagram. So we again start with a basic figure set. In this case, the basic figure set would involve ellipses as well, because they are pretty important for analytical geometry questions. So the basic figure set for analytical geometry problems would involve the same ones as the plane geometry ones, followed by some special diagrams as well, such as ellipses. So after that, we can choose a number of figures that need to be drawn, such as in this case, we'd have 4 figures that need to be drawn. And finally, we choose an area in which we want to draw the diagrams. For example, we'd want to draw this in the top left region in the graph. So this is how we generate an analytical geometry diagram. Now, drawing a function diagram using the data engine is pretty simple because we're just graphing a particular function in this case. And we can just label some special points in the function geometry in the function diagram. So we just used a data engine in order to generate data from the 3 fields of plane geometry, analytical geometry, and functions. After that, like I said, we needed 2 special data sets known as MAVIS caption and MAVIS instruct. MAVIS caption was a special data set in order to generate captions for a particular diagram. So let's just go through how MAVIS caption works. This mainly employs the use of GPT-4. GPT-4 is used to create prompts. So as can be seen in table 1, the total number of plane geometry diagrams that MAVIS caption generates is 299K, analytical geometry diagrams is 77K, and function diagrams is 212K. We'd have the length of the words that it generates, which are the captions for the particular diagram. So again, we need to discuss how we generate diagrams in 3 cases for plane geometry, analytical geometry, and functions. So in the case of plane geometry diagrams, such as these plane geometry diagrams, we use GPT-4 to in order to have 3 templates. First, we need to understand the basic fundamental shapes, such as the 3 shapes ABCD, BCEF, and BEHI. These are the 3 fundamental shapes in the diagram. After that, we would label certain specific attributes inside the diagram, such as the right angle located at A, the length of side AB, length of side BC. After we have used these 2, we'd like to mention that BCEF is located to the bottom of ABCD and so on. So this would help us generate a caption for this particular diagram. This is involved for plane geometry. Then for analytical geometry, again, we mainly just need the coordinates, followed by certain attributes of the shape and the spatial location of the various shapes. This is how you can generate a caption in analytical geometry. And to generate a caption with functions, it's very simple. You just need to generate various properties of the function because a function is mathematically defined. So we can just generate various properties of a function involving, let's say, the minimum or the 0 points of the function. So this, yeah, yeah, sure. Like I said. So we first need the descriptive content of the fundamental shapes. So for plane geometry, right? When we're generating captions for plane geometry, oh, so are you talking about analytical geometry or for functions? Okay, right. So yeah. So you can, like, they talk about, you can talk about the coordinates and the attribute of the particular shape, and you can talk about the spatial location of the shape, right? So the coordinates that are involved and the shape followed by the spatial location of the shape. Those are the two templates. For example, in this case, uh, there's um, there's a description of the particular square with base left corner at this coordinate and this side length, and this is the spatial relation for a figure that's nearby. So that's a caption for analytical geometry. Um, After we talked about the MAVIS caption dataset, which mainly involved us generating a caption for a particular diagram, um, we can we have the MAVIS instruct dataset. The MAVIS instruct dataset mainly helps the LLM for problem solving skills, and this mainly puts the analytical geometry inside functional questions. So in MAVIS instruct, each prompt, such as this part here, has a chain of thought that is involved in order to solve the problem. And usually, this chain of thought is of 150 words. So let's just go through the various sources which Mavis Instruct needs to generate the data set. Mavis Instruct mainly uses four sources of information: manual collection with the help of GPT-4, uh, augmenting existing data sets with the help of GPT-4, uh, providing captions for this, sorry, providing using the data engine that we already discussed and using GPT-4 in order to annotate the specific diagrams generated by the data engine. And finally, having the data engine generate specific prompts on its own. So in the case of manual collection with the help of GPT-4, we would mainly have, so we first collect a set of 4K math prompts, and we generate 84K math prompts from the 4K math prompts. So this uses eight humans from and collects information from certain public sources. So some public sources from which we can collect the data are sites like these, which is called study.com, the site called mathspace.code/us. So these are two sites from which we collect the data. And then we use GPT in order to generate more questions. So you can look at figure 11. As can be seen here, this was the original question. The top is the original question that was collected from the data set. And then we use GPT in order to generate further such questions. Some of them could be multiple choice, some of them could be free answer questions. So this is how we use GPT with the help of the original data set. Now, another way of generating more such questions is uh, no, it's already there in the data set. So it's already there in the data set, and then we use GPT mainly to generate more questions from the questions that are already there. So that's how. Uh, I think we use GPT. So we use the original chain of thought, and there's some detail about the diagram in the caption itself. So we use that plus the chain of thought that has been provided, and we use GPT to from those to get more chain of thought for this question. So right. So this was using GPT-4 in order for manual collection. Then we also have so the second source of information for MAVIS Instruct is by using already previously existing data sets. So some of the previously existing data sets are Geometry 3K and GeoQA. So this is geometry. This is Yeah, this is Geometry 3K data set, which comes with the prompt, the description, the choices, and uh, this is Geometry 3K. And we also have another similar data set known as GeoQA Plus. And we mainly use GPT in order to, again, generate more questions from the previously existing questions in the data set. For example, in figure 12, um, we design more questions from previously existing data sets. So these are the GPT generated data sets, followed by the analysis and the answer for the particular question. So um, this was just, so the previous two methods just involve GPT in order to generate more data and more questions. After that, we can also use GPT in order to annotate the various data engine captions. So this is basically done with the help, as can be seen in figure 20 and figure 21. Where this was the diagram that was previously there, and this was the caption that was generated by the data engine. And then we use GPT-4 in order to generate the question and the analysis for the particular question. And then finally, we can also use the data engine to solve, to generate prompts themselves. So we again use the data engine to generate prompts in three particular scenarios: plane geometry, analytical geometry, and functions. In the case of plane geometry, uh, right, in the case of plane geometry, you can see in figure 14 to 19 how the data engine is used in order to generate more prompts. So we originally have a prompt from the data engine, and then we just ask questions regarding what the perimeter is, what the area is, and what the base length is in order to generate more questions with the help of the data engine. So this was how we generated the MAVIS instruct dataset, and we previously generated the MAVIS caption dataset. Now let's go through the training process of the model. So this model uses a clip. So first we need to understand what clip is. Clip mainly stands for contrastive language image pre-training. This consists of two separate neural networks, such as a text encoder and an image encoder. And one network is for processing the image, and the other is for processing the text. And you convert it into a vector such that the image is matched with its own text, with the text that is closest to it. And this mainly uses contrastive learning, which involves a contrastive loss function in order to bring the image and the text closer. So now that we have understood what clip is, we can go back to mathematical visual instruction tuning. So in this, we first want to train clip math, which is a special type of clip which mainly involves mathematical visual prompts. And for this, we use the MAVIS caption dataset, which we already had, which involved the images along with the captions that were previously mentioned. The captions involve the description of the image. Yeah. So right. So now we use clip math, which has a visual encoder in order to encode the particular information inside the diagram into the language. So for example, this is how clip works, where it takes an image encoder and a text encoder and tries to match the image with the particular text. But in this case, we'd mainly be providing it with a mathematical diagram along with the caption from the MAVIS caption dataset. And we would be aligning the caption with the diagram. So this was how clip math works. And clip math, as I already said, it's mainly introduced for encoding mathematical diagrams. Mainly involved in encoding mathematical diagrams. And after having trained a specific vision encoder mainly for mathematical diagrams, we'd like to align the encoding from the clip math along with the LLM. And this is mainly done with the help of so the main reason why we do this is because we want the LLM to solve mathematical questions on the basis of the diagram. So we need to make sure that the tokens from the clip math that we already introduced previously are put inside the LLM so that the LLM can solve mathematical problems. So the way this works is by using a two-layer MLP, which is called a multi-layer perceptron. So we transform the encodings from the clip math and pass it through the MLP, and we use the output appended to the input of the LLM. And this is how we try and align the diagram along with the LLM. And in this case, we just train the MLP along with the LLM in order to align the diagram with the language. Finally, there's the final stage of training where we want to allow the LLM to finally solve the mathematical problem. And this is done with the help of the MAVIS instruct dataset, which we previously introduced, which had the problem along with the solution. And in this case, the LLM that we use is a LoRa-based LLM, and we mainly train both the projection layer and the LLM with the MAVIS caption dataset that MAVIS instruct dataset that we previously introduced in order to help the LLM solve the problem. So this was the training that was introduced. So we have talked about the data sets that were introduced, which were MAVIS caption and MAVIS instruct, followed by the three-stage training process in order to train the LLM. Mm-hmm. Or just using the LLM? Or sorry, can you say that again? Mm-hmm. Yeah. Um, I think what you're saying works. The main reason why they're fixing the encoder is because we are just concentrating on training the LLM now. So we don't want to like affect the encoding previously that we already generated from the diagram. So that's the main reason they are trying to freeze the vision encoder while training the LLM. So I feel like what you're saying would be much better than what they've done in the paper. So, rather than just training it piecewise. Right? Mm-hmm. Yeah. So yeah, after we've discussed the method, we can look at some of the results that have been generated. Mavis 7B, which is the model that has been introduced by the paper, obviously performs the best among the rest of the LLMs in order to solve math. I mean, we're done anyways. Discuss the method and just that in the results we can see that Mavis 7B performs much better compared to most open source LLMs. So yeah. Which ones? Not Visual Sketchboard.
Maybe you can just say it.
Do you have the results for Visual Sketchboard paper?
Yeah, I think we can end it with it. We just saw the last slide.
Oh, sure. There's-
Okay, so thank you all for attending and make sure to follow us on social media so you can be aware of our next event. We'll probably have another talk on next Saturday from 11 to 12. Sorry, from 12 to 1. We'll update you about the room information soon, somewhere on our social media. So make sure to follow us. Thank you.